In this video, I am going to explain magnetic dipole moment of a revolving electron. You know, a circular coil carrying current will have magnetic dipole moment. The magnetic dipole moment of a current carrying coil is given by this relation Pm vector is equal to I into A vector. In magnitude, we can write Pm is equal to I into A, current multiplied by area of the coil. Now, when an electron is revolving, it will have magnetic dipole moment. So, electron, there are two types of motion, orbital motion and spin motion. We are going to consider the orbital motion in this video. Magnetic moment due to orbital motion, mu L vector is equal to I into A, where I is the current, A is the area. Now, area is a vector quantity, but in magnitude we can write mu L is equal to I into A. Then we have to get an expression for I, current. Current is rate of flow of charge, so Q by T. Here, charge of the electron is minus E divided by T, where T is the period. Period is the time taken by the electron to make one revolution. Now, period T is equal to 2 pi r divided by V. 2 pi r is the circumference of this circle. You divide by the velocity of the electron, so you will get the period. Now, you can substitute for this T. I is equal to minus E divided by, for this T, 2 pi r divided by V. That V can be taken to the numerator. So, we are getting an expression for current. Now, we can substitute mu L. So, in magnitude, mu L is I into A. For this I, we can substitute minus EV by 2 pi r. Then area is pi r square. So, now this pi will get cancelled. Then r square, here r, so 1 r will get cancelled. So, minus EVR by 2. So, that is the expression for magnetic dipole moment. Magnetic dipole moment of a revolving electron. Then electron, there is mass, so it will have linear momentum. Since it is going in a circular orbit, it will have angular momentum. So angular momentum L is r vector cross p vector. P vector is mass multiplied by velocity vector. So this is the velocity. In the direction of the velocity, this is r. So r vector cross p vector, r cross p. It is directed along this direction. It is directed in this direction upwards. This L vector. Then in magnitude, we can write L is equal to r into p. P is mass into velocity, then this r. So angular momentum is mv r. Then magnetic moment is directed downwards. So angular momentum and the magnetic moment are in the opposite direction. Here you can see a negative sign. So here angular momentum is in the upward direction. Then magnetic moment is in the downward direction. They are in the opposite direction. Now let us make a comparison between magnetic moment and angular momentum of the electron. So you divide this by this. So mu L by L. Magnetic dipole moment of a revolving electron is given by this relation. Mu L is minus EVR by 2. Angular momentum of the electron is MVR. You divide mu L by L. Then when you divide this, VR and VR will get cancelled. So it will be minus E by 2m. Then substitute the values. Charge of the electron 1.6 into 10 raised to minus 19 coulomb. Mass of the electron 9.11 into 10 raised to minus 31. When we consider the magnitude, this negative sign is not needed. Then when you do this calculation, you will get 8.78 into 10 raised to 10 coulomb per kg. We are comparing the magnetic moment to angular momentum, and this quantity is a constant, and this is known as gyromagnetic ratio. According to Niels Bohr, angular momentum of an electron in an orbit is quantized. That means it will be multiple of h by 2 pi. Angular momentum L is equal to n times h by 2 pi, where h is the Planck's constant, 6.63 into 10 raised to minus 34 joule second. Now you know gyromagnetic ratio. Mu L is the magnetic moment of the revolving electron. L is the angular momentum. Gyromagnetic ratio is E by 2m. So from this we can write mu L is E by 2m into L. For this L we can substitute this nh by 2 pi. So mu L is E by 2m into L. For L we can write nh by 2 pi. So it is NEH by 4 pi m. Here 2 into 2 4, so it is 4 pi am. Then magnetic moment unit is ampere meter square, because magnetic moment is current multiplied by area. Current ampere, area meter square. So mu L is NEH by 4 pi m. Now you can substitute all these values. N is the number of the orbit. When an electron is in the first orbit, n is 1, second orbit 2. The other values you substitute. Charge of the electron 1.6 now into 10 raised to minus 19. Planck's constant 6.63 into 10 raised to minus 34. Mass of the electron 9.11 into 10 raised to minus 31. So when you substitute the values and do the calculation, you will get a 9.27 into 10 raised to minus 24. Then this n is the number of the orbits. First orbit, n is 1. Then this will have minimum value when electron is in the first orbit. So when you substitute, n is equal to 1 in this expression, EH by 4 pi m. That is what is called Bohr magneton. Its value is 9.27 into 10 raised to minus 24. When you substitute n is equal to 1, you will get this value. This is what is known as Bohr magneton. Thank you for watching.